Okay, so here's my original circuit. All right. Okay, so hang on to those numbers. I'm going to clean this up just a bit. Okay, hang on to those numbers. I'm just going to solve this thing using traditional methods. Okay, so let's get in here with blue. I'm going to say 1k ohm, 4.7k ohm, 2.2k ohm, 25 volts applied, and there we go. So I know I'm going to find an equivalency right here, and then I'm going to find our total with those two values in series. So let's just rip through this real quick. Okay, so our total of my original circuit, okay, is going to be R1 in series with Req. Okay, well, let's figure out what Req is. Req equals 1 over. This is just how you see it in your, when you go look, the 1 over, the sum of the conductances, and then reciprocal to get back to resistance. Let's look. So R2 plus R3. Okay. Alright, so parallel rules. Okay, 1 over 4.7k plus 1 over 2.2k. So my number's definitely going to be smaller than my smallest branch. So let's look. Bring the old calculator just to show it. Okay, clear. So 1 divided by a couple of parentheses. 4.7k. Alright, let's keep that number, plus, not times, 1 divided by 2.2k, get old R3 in there. Alright, let's see what our calculator says. So the formula looks like it fell into place properly, and my equivalent network is 1.499 k ohms, so just about 1500. Just about 1.5k. So now let's add in our 1k. So our total equals, and I've got the formula up here, our total equals R1 1k plus Req, which was 1.499k ohms. So our total is going to be 2.499k ohms. That's nice. Alright, so now I can find current. It's getting exciting, don't you think? You're like, yeah, real exciting. Okay, so I can find my total current, IT, and then I know I'm going to have IR2 here, IR3 here, okay, and here, and here, and IT again. Going through R1. So R1 is definitely going to see I total. The parallel network we're going to have to think about a little bit more. I total equals V total over R total. Just back to Ohm's law. I total equals that 25 volts that we had applied to the circuit over R total, which we found to be 2.499 k ohms. So I total is going to be a number, clear. Okay, 25 divided by our less rounded resistance gives me 16.68 milliamps. So that is super good. Okay, now I can find the voltage of R1. Let's do it in green, just to keep things kind of separated. So VR1 is I total, as it shows with my current pass, times R1. VR1 equals, I'm going to say 16.68 volts. Oops, I forgot a step. 16.68 milliamps. So 10 to the minus third times 1k ohms, which is 10 to the third. So those cancel. I should just get this number. What do you say we just check that? Okay, clear, enter times 1 e to the third. And sure enough, it comes out. Whoa, that was a crazy. That happened. So my calculator got huge, so that's cool. Let's get that thing back down under control here. Alright. Okay, well, let's find the voltage over our equivalent network. Why not? So V of REQ, it's just a simple matter of IT times that REQ value that we found earlier. V REQ equals, now you're going to see hopefully a familiar number here, 16.68 milliamps times 1.499 k ohms. VREQ equals, let's just see how it goes. Okay, come on calculator. Okay, so let's get that current total times our equivalent resistor, which we found up here someplace. Let's go find it. There it is. Less rounded. Oh boy, that is not my number that I wanted. Oh, what have I done? Oh, I see. I made a mistake. Look at that. Look at that. I made a mistake. So I did my REQ, not my R total, right here. Look at that. Look at that. Okay, let's get that fixed. Alright, so my current, look at that. My current is wrong. So I total is not that, because I wrote it down. I wrote it down properly, which makes troubleshooting lots of fun. So I total corrected is 10.01 milliamps. Okay, so that makes that number wrong and that number wrong. So VR1 equals 10.01 milliamps times 1k ohms. Okay, look at that. So that's wrong. And alright, so VR1 equals 10.01 volts. Alright, let's clean that up a little bit. Yeah, so it's that easy to make a mistake. I don't know if you caught it when I was doing that. I mean, hopefully you're paying attention or trying to beat me done. Okay, so let's do this. So V REQ equals 10.01 milliamps times 1.499 k ohms. Alright, let's find that VREQ number. Alright, come on calc. Alright. So now the calculator just does what you tell it. So VREQ is going to be that number times the actual, that 14 number. Let's look for it. There it is. The less rounded version. So VREQ should be 14.99 volts. There it is. Okay, so let's write that. Okay, so that's cool. So very familiar number. Let's just check those currents and let's just finish this out and see. So now IR2 can be found. IR2 can be found. Now look at I'm going to Kirchhoff this in a second. So IR2 is going to be VREQ over R2's number. Okay, IR2 equals 14.99 volts over R2, which is 4.7 k ohms. Okay, so IR2 equals, calculator, that voltage less rounded divided by 4.7. Whoa, that easy. e to the third. IR2 is 3.19 milliamps. Okay, same thing for IR3. Alright. VREQ, because it's the same voltage in parallel as R2, over R3's value this time. IR3 equals 14.99 volts over 2.2k ohms. So IR3 equals, here we go, calculator. Here we go, let's see what it is. That voltage less rounded divided by 2.2 e to the third. Got that in there good. And here's our 6.816 milliamps. Now remember, let's come in here with a different color here, brighter color. So that's the voltage. Now I just solved this whole thing using standard Ohm's law and parallel techniques. Here's the voltage and the current of R3. Now let's compare that. So we did Thevenin analysis before. Let's see what we got. Look at that. 6.815 milliamps and 14.99 volts. Ta-da! So that is strangely familiar to our, okay, so we feel good. We got the same numbers. Now I could Kirchhoff this out. Basically, VR1 is 10 volts plus 14.99, so that sums to 25. So Kirchhoff's happy with that number and that number. These two should sum to our total current, which was 10.01 milliamps. Well, let's not do that in our head. I might be able to, but maybe not. So there's our IR3 plus, enter plus. Where's our IR2? So if they sum to the total current, then Kirchhoff's happy and everybody's happy. 10.01 milliamps, boom, double checked. Okay, so there's Thevenin's analysis and proof that it gets you the same numbers. Now you would do this if you had a complex network that you didn't want to solve the standard way over and over, and you could try out different values for your loads. You could, there's some circuits that are a little bit difficult to solve using standard Ohm's law Kirchhoff method, so this may provide an easier method for some difficult circuits, and we'll look at that here in another video. But this has been a quick run through, an introduction of using Thevenin's analysis to solve a series parallel circuit, and we solved it using Ohm's law in the end, and all of our numbers matched, so it feels pretty good. So remember your steps. Original circuit, find our Thevenin. So you're going to find the resistance that the load would see looking back at the rest of the circuit. Open or remove the load, define the A and B points, which pretty much is where the load was. Where did it come from, or where was it in your circuit? Short out that power supply to provide that 0 ohm path where the power supply is, and then just calculate the resistance between A and B. So that is the resistance of the rest of the circuit as far as that load is concerned. Okay, V Thevenin. Alright, so we're just looking at the most voltage that the A and B points could ever see in your original circuit. So take that load out and measure where it was, and you will see a value for V Thevenin. So the steps, V Thevenin is the most voltage that your given circuit could ever provide between A and B, and so therefore if you open or remove the load, you will basically have the maximum resistance of that load. Simulate it by putting in, I don't know, put your meter in there, a 10 mega ohm resistor, so you can actually see your voltmeter number. All right, and so you can see what the biggest resistance you got would be there. Okay, so then solve that circuit, find keep all your original values, solve that circuit without that load resistor in there, and then the voltage between your A and B points is your Thevenin. And what do you do with that? All that? Well, once you have all that, you can create your equivalent Thevenin circuit, where you apply Thevenin, which is the most voltage available to any value for your load. And then your circuit resistance, as far as the load is concerned, is in series. That's where our Thevenin goes. And then when you solve this little circuit, the voltage and the current and the resistance for R3 are going to be the same as in the original circuit. So you could do Thevenin's analysis now confidently and not solve the original circuit and know that that target resistor is going to see that voltage, okay, and that current in the original circuit. So you can calculate this, and then you can build the original. I'll be darned, it's gonna do exactly what Thevenin's analysis shows you. Okay, so all right, well, that's it. I'm gonna leave it right there, and I'll do another video with a more complicated circuit, maybe a unbalanced bridge.